Okay, so let me start by thanking the organizers and also congratulating them on the wonderful new center. So I'll talk about some recent work that I've done, mostly based on this paper. Some earlier papers, some things didn't make it to the final paper, but I think this is the one that I'm going to talk about here. So I'll start by just distinguishing what I mean by the superstring. So of course, I'll call the RNS string the spinning string just to distinguish it. So of course, the RNS string has fermions, but they're space-time vectors instead of space-time spinners. And they're worldsheet spinners instead of worldsheet scalars. So in some sense, the spinning string, the fermions are natural from the worldsheet point of view, but not from the space-time point of view, because of course, they're anti-commuting. Whereas in the superstring, the opposite is true. So the fermions are natural from the space-time point of view, but not from the worldsheet point of view. Now, of course, the spinning string has manifest worldsheet supersymmetry. The fields transform linearly under worldsheet supersymmetry, at least in the Navier-Schwarz sector. So the GSO plus and GSO minus sector for the Navier-Schwarz, so for example, the tachyon is in the GSO minus Navier-Schwarz sector. Worldsheet supersymmetry transforms in a simple way, and essentially the formalism is much easier to define in that sector. So when you try to define it in the Ramon sector, it's more complicated. In fact, people still don't know how to describe Ramon backgrounds in this theory, which is, of course, an important thing you want to describe. Of course, there are other things we don't know how to describe. So, for example, the D equals 11 supermembrane, we really don't have a spinning string or a spinning membrane version of this. We can compute multi-loop amplitudes. So, of course, Doku and Fong computed the two-loop 4-point amplitude, at least for 4 Navier-Schwarz states. So in the superstring, of course, there are other backgrounds that are more difficult to describe. We know how to have manifest space-time supersymmetry in the GSO plus sector. So that's perfect if we want to describe supergravity. But if we want to describe, for example, tachyonic backgrounds, it's much more complicated in the superstring. So in some sense, it's the analog of the Ramon states in the spinning string. And we still only know how to describe really backgrounds which are backgrounds of 10-dimensional supergravity. We don't know how to describe, for example, non-critical backgrounds in this theory. So although these two theories are supposed to be equivalent, we really only know how to describe them in an equivalent way in the Navier-Schwarz GSO plus sector. Now, there have, of course, also been multi-loop amplitudes in this formalism. So the two-loop 4-point was done soon after Doku and Fong, and then it was extended. So the coefficient of the two-loop and 4-point were computed by Humberto Gomez and Carlos Mafra, and now they've been able to compute the 3-loop 4-point that was reported on last year at Strings, and in fact, recently they found the correct coefficient that's consistent with S-duality, and was extended more recently to the two-loop 5-point together with Oliver Schlotl. So there are lots of things that can be done using the superstring, and it's worthwhile to study. Okay, so let me give a quick review of the superstring. So first, the Green-Schwarz formalism. So there are x and theta hat variables. I'll just do type 2. And you can do type 2a or type 2b, depending if alpha and alpha hat have the same chirality or opposite chirality. So this is the usual Green-Schwarz covariant action. And when you do canonical quantization, so you define the canonical momentum for theta, you find it's not independent of theta itself. You have a constraint. The constraint I'll call d alpha. It has a first class and a second class piece. That can be seen because the anti-commutator is not 0. But prior to it is 0 once you use the Virasoro constraint. So it turns out to have 8 first class and 8 second class fermionic constraints. The first class constraint generate this local fermionic kappa symmetry that John mentioned. The second class constraints are more complicated to deal with. So you can quantize in light cone gauge where you solve them. But if you try to quantize covariantly, essentially it's an unsolved problem how to do this. So this is the Green-Schwarz formalism in its covariant formulation. And this, more recently, this pure spinor formalism. So the variables are slightly different. We have the x variable. We have theta together with its conjugate momentum. So unlike in Green-Schwarz, where this is dependent on theta, now we think of them as independent variables. So this was first discussed by Warren Siegel. Then you also have some variables which you can naturally interpret as ghosts in the sense that they're bosonic. So lambda and lambda hat are bosonic space-time spinners. But they're going to be constrained space-time spinners, which Cartan called pure spinners. So they satisfy this constraint. It means that they parameterize this space. So it's SO10 over U5. That has 10 complex directions, but then you also have a complex scale factor. So it's just a free action, at least if you're in a flat background. And it's easy to compute the conformal anomaly just because they're all conformal weight 0 and 1. So these contribute plus 10, these contribute minus 32, and these contribute plus 22. You can also define physical states. You have to introduce this BRST operator, which naively looks like, well, it is just the Green-Schwarz Dirac constraint times this pure spinor ghost. So that's another reason why you might want to call this a ghost variable. And you can easily see that Q squared is nilpotent using the lambda gamma lambda equals 0 condition. Now the open string state is going to be defined as something in the cohomology ghost number 1. So the only you can construct, which doesn't depend on the non-zero, on the world sheet non-zero mode, is just this type of spinor superfield. And it turns out when you ask the QV equals 0, this describes on-shell super Yang-Mills. And when you do for the supergravity sector, for the closed string, you just get a bispinor. Sorry. So this describes supergravity. Okay, I think the battery is running out on the light, on the pointer. So a natural question is, where does this BRST operator come from? So naively, you'd want to get it from gauge fixing something. And so the natural thing to try to do is to get it from Green-Schwarz, where d alpha is the constraint and lambda alpha is the ghost. So a question that I'll address in this talk is, what is the origin of this Q? Now, it turns out this naive guess doesn't seem to work. So this lambda alpha ghost is, of course, constrained. And it's very difficult to see how you can get the constrained bosonic ghost from gauge fixing a fermionic symmetry. Although me and many people have tried, I don't think we really succeeded. Secondly, you have this Virasoro ghost, which you would expect to get if you start with some world sheet reparameterization invariant action, and they're not present in Q. Thirdly, you have this field theta, which is a world sheet scalar, which actually sounds like it's a world sheet ghost and not a world sheet matter field. Okay, now these ideas also will be related to the fact that the super Yang-Mills and supergravity equations of motion, thank you. Thanks. Were first shown, in fact, by Witten in '86, that integrability along light-like lines gives the super Yang-Mills equations of motion and supergravity equations of motion. And Paul House showed that integrability of pure spinor lines. And in fact, this was the first place that twistors appeared in this approach to first for Green-Schwarz and also for pure spinors, and was later shown by Sorkin and many collaborators are useful for understanding this kappa symmetry. So now we have twistors appearing in the game, and it turns out twistors are nothing but, if you look in higher dimensions, in even dimensions, pure spinors are nothing but twistors. So they parameterize this space if you think about a projective pure spinor. So I don't have any more the scale part. In fact, this was shown a long time ago by Houston to be the natural higher dimensional generalization of Penrose twistors in four dimensions. Another clue is that this theory just has bosonic and fermions of conformal weight 0 and 1, as in topological strings. And furthermore, twisted versions of d equals 10 super Yang-Mills and supergravity have been recently related to c hat equals 5 topological theories, so by these people. So all of these ideas will come together in this proposal for the origin of Q. So the proposal is, suppose you start with c hat equals 5 topological A or B model. So that, of course, requires a choice of the complex structure. So SO10 over U5 is this choice, and that's precisely what the pure spinors do. They choose an SO10 over U5. So the claim is that the classical action for the type 2A or type 2B superstring just comes from the topological A or B model, where you use the pure spinors to choose this choice of complex structure. So just to remind you what the topological A or B model, you can think of it as just a purely bosonic action before gauge fixing. So these are Lagrange multipliers for the left and right moving. So you choose 5 complex x's, or in general half of the complex. So you start with, let's say, d x's, and you choose d over 2 to be holomorphic and d over 2 to be anti-holomorphic. And when you gauge fix these Lagrange multipliers, you give rise to, of course, Faddeev-Popov ghosts, and these are the fermions of the model. So usually it's written in this form, but this is, of course, is related to this by just the usual BRST procedure. And in this case, the BRST operator is just written in this way in terms of the matter and the ghost fields. So now the idea is to replace these fermionic ghost fields with just the thetas. And the way that happens is you choose, instead of choosing dxa to be your constraint, now you choose a constraint which is 10-dimensionally convariant using the pure spinor. And L alpha is now, instead of LA, so alpha is now 1 to 16, are the Lagrange multipliers whose gauge fixing will give rise to the thetas. In addition, of course, you have to introduce a sector depending on the lambda variables, which are going to choose the directions. And as I already mentioned, gauge fixing the L is going to give you the Fadeev-Popov ghosts. And it will turn out that both the Green-Schwarz and the pure spinor actions you can obtain just by different choices of the gauge fixing. So different choices of this chi, of this gauge fixing fermion, will give you the Green-Schwarz or the pure spinors. And in the case of the pure spinor gauge fixing, this BRST operator is precisely what you want. Okay, so to show how this works, what I'll do is I'll do it first for the superparticle, just because the superparticle is much simpler. So in the pure spinor case, the superparticle is just composed of x's and these thetas and lambdas. In this case, you start with lambda. It's not a projective pure spinor. It's just a pure spinor. So there's a scale part. And this is the BRST operator. And these are the BRST transformations. Now, as I already mentioned, the cohomology of ghost number 1 is just given by this vertex operator. And it's easy to expand out this superfield and show that when the vertex operator is annihilated by Q, it's just related to the usual on-shell super-Yang-Mills field. So Green-Schwarz is also simple. It's not quadratic anymore. But again, there's a fermionic constraint which generates kappa symmetry. And these are the kappa transformations, which don't look so different from the BRST transformations, and in fact, they will be related. In this case, as in the superstring, covariant quantization is complicated. It's not as complicated as a superstring, but it's trivial to get the spectrum just by using light cone analysis. Okay, so let's see how it works for the superparticle. So the Twistor-like version of the superparticle will be obtained by replacing the usual mass shell constraint by this Twistor-like constraint. So this, of course, implies p squared equals 0, but it does more. It implies a whole spinor worth of constraints. So L alpha is going to be the Lagrange multiplier, which imposes this constraint. Okay, so now, unlike in the pure spinor version, this lambda is projective. So what that means is that I have to introduce a gauge field on the world line and define lambda to be identified if I do a scale transformation on lambda, and obviously analogous scale transformations on L and on W. Okay, so of course this symmetry has gauge transformations generated p slash lambda. These are the gauge transformations. And in addition, there's an additional gauge transformation coming from the lambda gamma lambda equals 0 constraint, which means that if I scale lambda by this, if I shift lambda by this amount, the action is also invariant. Because of this extra term, there's a gauge for gauge transformation. So I can shift theta and cancel that by a shift of psi. And so this is how that works. It almost cancels. There's a term left over, which is del lambda, which has to be canceled by a shift of W. So this is the shift of W, and chi is the gauge fixing fermion. So the reason why you have to shift W is because this shift is only this delta squared of this is 0 only up to a equation of motion for lambda. Okay, so of course when you do the BRST quantization, this theta and psi become fermions, so the fermionic ghosts. And phi, this field coming from the ghost for the gauge for gauge transformation, is bosonic. And of course these also scale in accordance with the scale transformations of lambda. And this is the gauge fixed action, and these are the BRST transformations which you can read off from these gauge transformation and gauge for gauge transformation. Okay, so this is the particle action before gauge fixing, and now we're going to show how its gauge fixing gives rise to the pure spinor and Green-Schwarz versions. Okay, so the pure spinor version in some sense is simpler. You choose the gauge fixing fermion to be proportional to the Lagrange multiplier, so that means you just gauge L alpha to be 0, and you also gauge Xi equals 0. So P alpha is a fermionic antighost and beta is a bosonic antighost. And these, as in the usual BRST procedure, they transform into Nakanishi-Lautrup fields, whose BRST variation is 0. So you can just compute the gauge fixed action using the usual BRST gauge fixing procedure, and this is what we get. Now there's one more important ingredient, which is that we still have this scale symmetry. So naively, you would use the scale symmetry to gauge fix one of the components of lambda to 1. In this case, I'm going to do something different. Of course, scaling one of the components to lambda to 1 would break the Lorentz invariance. So I'm going to scale phi to 1. So this, of course, is only possible if I assume that phi is nowhere vanishing. So we're going to make this assumption. And that means we can scale phi to 1. But phi, remember, carries ghost number. It's a ghost for ghost, so it carries ghost number 2. And furthermore, it carries scale weight, so it's not scale invariant, which means that when I do this gauge fixing, all the fields which have a certain ghost number or a certain ghost number are going to be shifted, because this object here is easily shown to be scale invariant. So if this operator has scale invariant, scales with weight s and has ghost number g, this operator here is scale invariant, because this operator here scales with, has scale weight minus s. So this operator is scale invariant, but now it has ghost number g plus s, because this has ghost number 2, phi. So the ghost number is just shifted by the scale weight. This has ghost number g plus s, which means that theta, it started out with ghost number 1, but because it has scale weight minus 1, it now has ghost number 0 after this gauge fix. Similarly, lambda started out with ghost number 0, but because it has scale weight 1, it has ghost number 1. So we've shifted the ghost number. The action is, of course, the same as here. We've just used the auxiliary equations of motion that fixes the world line gauge field to be 0. So this just becomes the ordinary time derivative. So this is just the usual pure spinor action. And the BRST operator, it's easy to read off from the original BRST transformation, is just the BRST operator you want. Okay, so that's the gauge fixing to the pure spinor superparticle. For the Green-Schwarz, it's slightly more complicated, because essentially you want to get rid of this W and lambda field. So what you choose is the gauge fixing fermion such that the BRST variation of W is 0. So that's possible because the BRST variation of W depends on chi. So you choose it this way. This term here allows you to get rid of the term W del lambda. So after doing this gauge fixing here, the action takes this form. This is not quite the superparticle of the Green-Schwarz, because it has this extra term here. So we're going to do the same gauge fixing of the scale symmetry. So after fixing phi equals 1, theta again has ghost number 0. So you have this term, what you wanted, but you have, instead of the term E times P squared, now you have this L alpha times P slash lambda. So of course the equation of motion from this is that P slash lambda equals 0, which implies not only that P squared equals 0, but that you can write lambda as P slash of something. And this something is going to be precisely the kappa parameter. So in that case, the BRST transformations that we had before turn into precisely the kappa transformations, except that you don't have any more the variation of E in the kappa transformations of the Green-Schwarz superparticle. That's replaced by the variation of L. Okay, so this is the Green-Schwarz superparticle. It turns out the Noether charge coming from these BRST transformations is 0 in this case, which means that actually kappa is a local symmetry. So you haven't completely gauge fixed here. So that's how to get the Green-Schwarz superparticle. Okay, now let's go to the string. So this is going to be slightly more complicated, but it's the same idea. So in this case, we're going to replace the Virasoro constraints, which of course can be written in first order form in this form. So now we're going to replace the left moving and right moving by these combinations of P and D sigma x and lambda hat. And it turns out you also need additional constraints because the algebra of these don't close. So these constraints imply, if you want to close the algebra, that del sigma of lambda and del sigma of lambda hat is also 0. So in first order form, these are the constraints. And now, although this is written in first order form, it's not manifestly Wiltshire reparameterization invariant. If you want, you can do a shift of L and L hat and integrate out P, and then you can write it in a manifestly Wiltshire reparameterization invariant form. Okay, again, you can choose the gauge fixing fermion, and I'm not going to do it, but this is in the paper that I wrote, in order that you land on the pure spinor action and the Green-Schwarz action. And again, in the Green-Schwarz case, you find that the Noether charge is 0. In the pure spinor case, you find that the Noether charge for the BRST transformations is precisely what you want. Sorry, how much time do I have? Okay. Okay, again, we can do the supermembrane. We can also do the supermembrane. So it turns out that the superparticle version of the supermembrane, which is of course now in 11 dimensions. In this case, it turns out the D equals 11 superparticle describes not super Yang-Mills, it describes D equals 11 supergravity. The vertex operator which replaces this vertex operator for super Yang-Mills is now ghost number 3. And this is related to the 3 form of supergravity. Now it turns out that the constraints, the Virasoro constraints, which were written in Twistor-like form here in terms of P, can now be written in terms of the 11-dimensional pure spinors. So under double dimensional reduction, this just reduces, the 32 components of this reduce to the left and right moving twistor-like constraints we had for the superstring. And this turns out to be the analog of the twistor-like action for the supermembrane. Okay, so let me just summarize. So there are essentially four things we've shown. So the proposal is that you can get the classical. So it's classical because the fermions, the ghosts, are not yet in the theory. So the classical 2A and 2B superstring action are obtained just from the topological A and B model, C hat equals 5, by using these projective pure spinors to just choose the complex structure. So that's a rather elegant idea. In this case, the thetas come as fermionic ghosts from the gauge fixing. And in this case, the gauge fixing is of these twistor-like constraints instead of the Virasoro constraints. Now, the one other non-trivial feature is that you have to have a ghost for ghost which has a non-zero expectation value. So this allows you to shift the ghost number after setting this phi to be equal to 1, such that the fermions have ghost number 0 instead of ghost number 1. And that forces lambda to have ghost number 1. Okay, so what we've shown is for the superparticle of the superstring and supermembrane that this gauge fixing allows you to get not just pure spinor, but also the Green-Schwarz formalism. Okay, so I have some applications. So one application is, of course, to try to find other gauge fixings. One would like to, for example, try to gauge fix to the INS string. Maybe one can do this in certain backgrounds, or maybe to the Twistor string. So the Twistor string has been now developed for certain backgrounds, and maybe there's some clever gauge fixing in which you can get rid of all the x's instead of just, so you have, instead of x slash and lambda, maybe you can get just twistor variables. Another thing you would like to do is pure spinor formalism has a scattering amplitude prescription, which was used to compute these multi-loop amplitudes. It's easy to show it's BRST invariant, but it has some rather unusual features. So you need a regulator in order to do the integration over the pure spinors. We would like to derive this prescription starting from some reparameterization invariant formalism. Okay, thirdly, one would like to describe the superstring in backgrounds other than d equals 10 supergravity backgrounds. This sounds promising once you can start from something like a topological model. And finally, one would like to understand the relation of this to these twisted versions of supergravity and super-Yang-Mills. So there's a recent paper by Costello and Lee in which he showed that C hat equals 5, there's a BCOV, or Kodaira-Spencer theory, which is related to this twisted type 2A supergravity. And perhaps one might be able to, using this method, generalize it to the full closed superstring. Okay, so I'll stop.
The Euclidean version, I'm assuming.
Yes.
Have you thought about the Minkowski version and the connection with?
Yeah. So the easiest way to define the easiest way to define pure spinors is actually in signature 5,5. So in signature 5,5, you can define lambda to be all real components. So of course you can Wick rotate to Minkowski space, but in Minkowski space the reality conditions on lambda are more complicated. So in some sense, it's analogous to the SO2, 2 in 4 dimensions. So, but it's the SO5. I think of it always starting in SO5, 5 and then Wick rotating.
Other questions? Right. We'll break for coffee. Thank you very much. So you're to come back at 4 o'clock for the next session.